Yeah, hello, good evening, everyone. Yes, please confirm my audio and my screen sharing is clear. Yeah, thank you, everyone. So, the today's topic is the case study of sequential logic design. So, for the combinational logic design, we have selected the design or the project for the case study to discuss is a carry select adder using ripple carry adders, binary to XS1 converter, multiplexers. And we have done the simulation using EDA playground. Okay, the same way, coming to the sequential logic design. In sequential logic design, we have flip flops, counters, shift registers. So, combinedly, using a case study, I am going to explain you about random counter using linear feedback shift register. So, using one circuit, I am explaining both the concept about counters, okay, and shift registers. And apart from that, we have a combination of flip flops and logic gates also inside the random counter or LFSR when we see the architecture or logical diagram. Okay, so what is linear feedback shift register? So the applications of linear feedback shift registers are it is mainly used in cryptography. Cryptography is nothing but for encoding or decoding, especially if we are sending some amount of code, okay, that is made into a encryption and we have to decrypt it. So this kind of logic is called cryptography. And next is pseudo random pattern generation. Pseudo random means if we are passing some value like 1011 and it will be generating random numbers. It is 4 bit. So it will generate the random numbers between 0 to 50. If you are passing 4 bits. If you are passing 3 bits, it will generate the random numbers from 0 to 7. And next is pseudo noise sequence. So when we get the noise analysis in digital circuits, to detect the noise analysis, we are going to use LFS. And whitening sequence. Whitening sequence means we want to pass some test vectors for a design. That is, n number of test vectors we need to pass to the design randomly for testing the design. So we are using this circuit for whitening sequence. That is white box verification. This LFSR is also used as random counter, which will count digital values with fastness compared to our up counter, down counter, trim counter. Okay. So coming to the block diagram or the circuit diagram, digital circuit diagram. Okay. All the 4 D flip flops are connected with a positive edge triggered clock. Okay. And those are synchronous. And we have a reset pin and we have a XOR gate. Hope everyone is visible with the block diagram of linear feedback shift register. Okay. I am considering random counter of 4 bits. Okay, then what it has to represent? It has to count from 0 to 15. I am using 4 D flip flops with positive edge triggered flip flops, D flip flops. And there is a feedback which is connected for the XOR gate. And there is a reset pin to pass the initial value to the all the flip flops. Clear so far, everyone? If you have any doubts, please let me know in the circuit or in the logical diagram. If someone confirms, we'll proceed further. My audio and screen is clear, right? There is no response from others. Yes. So hope everyone is understanding. So XOR gate is the feedback. So if we pass 4 bits, 4 values to the D flip-flops, either it will be going to a up counter or a down counter or a ring counter. Okay. To make it as a random counter, we are going to use XOR operation. This is how the logic is designed. Clear? There was some question from someone. Hemant, did you understand? Okay, sir. Next. Coming to the Verilog part. Okay. So I'll put the complete code in a notepad. So the top level module name is LFSR, module LFSR. Input, clock, input, reset, and output, register as the output. DC. Okay. So the Q output is 4-bit. Always at the rate of positive edge of clock or positive edge of reset. Okay. So this is positive edge triggered D flip flops. Whatever the block diagram represents or the circuit diagram or logic diagram represents, all the flip flops are positive clock edge triggered. And next one is all the pins of the reset are connected. Okay. But the reset pin should be positive. That is, reset should be high. If reset is high, okay, the Q output should be 0001. If someone has question, please post it. Okay. Next. Else Q1 value should be passed to, I'll mention the Q0, Q1, Q2, Q3, and here the Q4 pin. Yes, yes. So next, this is Q4 output. Okay. So this kind of statement is non-blocking assignment. non-blocking assignment. So Q naught value is directly assigned to the Q1, and Q1 value is assigned to Q2, and Q2 value is assigned to Q3, and Q3 value is assigned to Q4. Okay, but what is the Q naught value? XOR of Q3 and Q4. Here we have Q4 as the output signal here, the wire output. Narendra Babu. So only I have written here Q0, Q1, Q2, Q3, and Q4. Okay. So the output Q0, Q4 is assigned directly to the out pin, and it is sent to the XOR of XOR gate. So the Q0 is equal to XOR of Q4 and Q3. And directly the out is equal to Q4. You can use both XOR or XNOR. Okay. So there are two conditions. So to generate the random pattern generation, you can use XOR gate or XNOR gate. So this is our test bench, TB underscore LFSR. Okay. Register clock, register reset, whereas the output, and the LFSR is the unit under test. That is module level. So we are connecting this test bench to LFSR using dot operator. That is clock pin to the clock pin, reset pin to the reset pin, and output to the output pin. If you, yes, good question, Sai Shankar. If you are using other gates, okay, just try with your experiment. If you are using NAND gate, NOR gate, or inverter, okay, how we are going to generate the patterns, whether they are sequential patterns or non-sequential patterns or random patterns, or it is counting the random numbers. Okay, just verify the output. As the EDA playground is free, open source. Okay, so instead of using the output XOR, you can directly write AND operator or OR operator or negation inverter. Just try this and observe the output and get the result, whether they are giving the LFSR, linear feedback shift register, as per the specification or as per the logical diagram, the output or not. Sai Shankar, will it be okay? Okay, sir. So if everything I am giving it to you clearly, you people are losing the exercise practice. So what you need to do is, whatever the code, whatever the logic diagram I'm giving, you just do some experiment with changing some values and understand what is its main functionality, and what if we change. It is random pattern generation, LFSR, the basic. Okay, so I'll show you the timing diagram, how the values are changed. So always with a unit of 5, this is free running clock, clock equal to negation of the clock. The clock period is 10 nanoseconds. That means the pulse width is 5 nanoseconds. This. And complete the clock cycle is 10 nanoseconds. Okay. Initial begin, the clock equal to 0 and reset equal to 1. After 100 units of delay, I am passing the value. Okay. Initial begin, dump VCD file and dump where TB LFSR. After 1000 milliseconds, I am checking what is my output. It should give some random pulses or random pattern. So let us try to compile this code and check. Okay, the file is saved by selecting the tools, simulator, and EP waveform, and the test bench and the design are written in Verilog. Okay. Now I am clicking run. Give me a minute. There is some registration issue with the IDA playground. Now run. So I'm passing a value 1. And if you see the values of Q4 down to 0, they are random. Okay, 2, 4, 8, 11, 3, 6, C, 19, 12, 5, 1, 2, 4, 8, 11. Not visible, sir. Now is it visible? The timing diagram here, Q4 to 4 down to 0. Okay, so the clock is there, free running clock, and whenever there is a reset 0, okay, here the reset is 0, then the random pattern generation gets started. That is 1, 2, 4, 8, 11, 3, 6, C, 19, 12. Okay, this is how the random pattern is generated. So if you pass some values intermediately like hexadecimal or some values, from there it will start to generate the random pattern generation. Hope everyone is clear so far. Understanding about LFSR design. Pawan Kumar Nayak. Yes, sir. Gupta, yes. If you have any questions, please let me know. And let's try. If we are putting some, okay, or get. Okay, I have saved the design and I am present. The output seems to be same. I think it didn't run. Similarly, try to do it your end. This is generating a very huge amount of random numbers. Okay, even it is 1E. And completely FF also. 1C. Try to experiment on this code and understand how are the results going to be. That's all. This is sequential circuit case study. Next is FSM. FSM is nothing but this is one of the last concept of sequential logic circuits. FSM is nothing but finite state machine. So we have two types of FSMs, that is Mille FSM and Moore FSM. So Mille state machine, it is a combinational logic circuit which has memory element and which has inputs and which has outputs. A finite state machine is said to be a Mille state machine if the output depends on both present input and the present state. Okay. So we have the current inputs and whatever the state of the logic. Okay. So both it depends, then it is called a Mille FSM. So the logic circuit example. Logic circuit value is 1 and the input value is 1. Okay. The output value will depend upon the present value and the inputs which we are passing in the current. Okay. This is how the Mille FSM is defined. Next. This is the state diagram. A, B, C are the three states. If I want to go from A to B, if it is 1, I will be transacting from A to B. If it is 0, I will be staying in the A value. If after reaching B, if I want to transact it from B to C, okay, the value passed is 0. If I am passing 1, it is staying in the B state. And after transacting to C, if I am passing a value 1, it is transacted to C. Else, if I am passing 0, it is transacted to A. So the Mille FSM is mainly depends on the present value and the inputs which we are passing. Next is Moore state machine. A finite state machine is said to be a Moore state machine if the output depends only on the present state. So we have some state S1. The S1 value is 1. Okay. Then the state is dependent on the present value. It is not depending on the previous value. The previous value might be anything. Either it is 0 or 1. Either we have 0 value or 1 value, but it is not depending on the previous value. It is depending on the present value, current data, whatever the data it is. Based on that data, it is going into next state. Then it is called a Moore state. Moore state machine is defined like this. This is a simple circuit description. Okay. So it has input and it has output, but it will depend only on the current input value. And it will proceed to the next stage. So the current value of A is 0. If it is taking the current value, it has to stay in the same position. If it is changing the value, it has to go to the next stage. The current value of B is 0. Okay. So only it is transacted to C. Else, if it is changing, it has to stay in the same position. The similar way, C, D, and if at all the values are changing, they are moving into the previous state and directly to the initial state. And here D is also moving to the intermediate stage. So this is how we define finite state machine. So here we have the typical example. If we consider 5 floors lift building, okay, we take an example of escalator or a lift, okay. We consider we are the lift is at a initial position of 0th floor, ground floor. Okay, there is no inside input or the outside input. And the person in the 4th floor has given the external input. There is no current value. The current value is 0. Okay. The present value, the 4th floor person has given the external input has to come to 4th floor directly. And if someone has boarded in the ground floor, they want to reach some other floor like 5th floor or 2nd floor or 1st floor. Then these kind of examples can work with FSM. Clear, everyone? This is a practical example how we use finite state machines. Whether it depends on the input, current state, previous state, or the next state. Clear so far, everyone? Please respond, someone. Whether you are understanding or not, I should know that. If you are not understanding, I need to explain it. Okay, thank you. The next concept, Moore FSM. So Moore FSM, the definition states that it depends only on the present state. So example, the lift is in ground floor and the 4th floor person has given the external input. Okay, what it is doing, it is depending only on the present state. And if we have any other person inside the lift and he has given some other input like 2nd floor, it will stop in the 2nd floor and move it to the 4th floor. But the 4th floor person has given as the first input. To save energy, it will stop in the 2nd floor and it will go to the 4th floor. And we can write a mixed mode of Verilog code using Moore FSM or Mille FSM. Clear, everyone? So far? Understood? So that we'll move to the next topic. Yes. So the current state is 0. So it is staying in the A state. And when it is having the input of present value is 1, then it is moving it to B state. And if the B value is 0, it is moving it to the C state. Else it will be 1. Then it has to stay in the B state. The C value is 0. Okay, it is passing it to D state. The D state value is 1. If it is 0, it has to come back to C. And if C value is 0, it has to come back to A. If D value is 1, it has to come back to B value. This is how Moore state machine works. What are these all are the inputs which we are passing it to the states. Based on the state value, whether it has to transact or it has to stay in the same position or it has to go to the previous state. This is how Moore state machines are designed. Clear, Sai Shankar? So how can we assume the input value? So it depends upon the user. So as we have taken example of the 5 floors of lift, so the lift is ideal which got settled in the ground floor initially. But the fourth floor person has given the input externally. Who is giving the input? User. So here these are assumption values, input values, whatever we are assuming. These are user inputs. User has to assume. If no fourth floor person has given the input externally, so someone has boarded in the lift and he has given second floor as the input. Then it will take the second floor input and it will drop in the second floor and then it will go to the external input fourth floor. This all depends upon the delay, timing, and power consumption. Clear, Sai Shankar? See, if the C value is 0, okay, if the input is 0 and C value is 0, then it is proceeding further. The D value is 1 and the input value is also 1. Then it is proceeding to the B state. The B state value is 1. If the C value is 0, where it has to go? It has to go to the A value. Clear? Hi Shankar, I understood why it is not going to the same state of C. If the C value is 0, where it has to go? It has to go to the A. A value is carrying 0. Understood? Sai Shankar. Yeah. Next. These are the most important topics. So whatever we have learned here, we also carrying see B also carrying 0. See the input value is 1, but the B is carrying 0. So if it is carrying 1, it has to stay in the same state. If it is carrying 0, it has to proceed further. Okay, current. Right. Should I proceed further? Okay. So whatever the concept we have learned so far is completely about front-end logic design. Now coming to the ASIC digital design flow and synthesis part. So after writing the Verilog code, after testing the functionality, the test bench is generated and the test cases are passed, then we have to go for this procedure. Okay, ASIC design flow. ASIC is nothing but application specific integrated circuit. If you have any questions, please stop me here. Intermediate. Okay, ASIC design flow diagram. The agenda is ASIC design flow explanation, tools used during each step, synthesis flow, inputs for synthesis. This is all related to the tool and its workaround. Timing constraints, outputs of synthesis, netlist example. Hope the agenda is clear for the session. Okay. So as we have initial class, what is IC? IC is the abbreviation of integrated circuits. Semiconductor chips are small semiconductor wafers that hold millions of tiny electronic components, whatever might be the electronic components, like resistors, capacitors, diodes, varactor diodes, tunnel diodes, or any kind of diodes, or MOS, NMOS, PMOS, BJT, any kind of device or electronic component. Those are fabricated on a semiconductor wafer. Then it is called an integrated circuits. All the circuits which are interconnected, okay, on a single die. Single die is nothing but the complete chip. The die we call it as single chip. Okay. IC fabrication. In simple terms, a semiconductor foundry, also known as a fab. Everyone knows this. Okay. This is a factory where silicon wafers are manufactured. You all might be knowing in the physics of semiconductor. Okay. They will collect the pure silicon. Okay. They will make it into a wafer by doping, N-type, P-type doping, and all those. They will do this in fab industry. Foundry required GDS 5 from IC design team to fabricate chip. GDS 2, GDS II or GDS 2. GDS is nothing but graphical data structure. So all we represent the chip design, circuit design in the layout, those all are graphics. That is nothing but it will have colorful layout diagram. That all GDS2 file, we have to send it to Fab City so that they will fabricate it on IC by using IC chip manufacturing tools. Okay, IC design is done using EDA applications. EDA application is nothing but electronic design automation. So some of the mechanical engineers, some of the civil engineers, what they are going to do? They are going to use some softwares for drawing the building structure. Okay, they are going to draw the motor dimensions in mechanical, or they are going to streamline the outer part of the car or aeroplane. Mechanical engineers. Similar way, the electronic engineers has a CAD application called EDA tools, electronic design automation tools. Helps in designing, optimizing area, power and timing, and verifying electronic circuits. Whatever the electronic circuit we design, like LFSR, okay, like counter, anything. So those all we are going to design, optimize area, timing, power. All this we are going to do, and we are sending it to the tab in the GDS2 format for fabrication. So far it's clear, right? Everyone. Someone please confirm. Hope everyone is with me. Yes. Coming to the integration scale. Okay. So we call the subject as VLSI, very large scale integration circuits. So very large scale integration circuits, those are categorized based on number of transistors or number of gates sitting on a single IC. IC is nothing but the chip size, whatever the chip size is. The chip size, if we are manufacturing the number of transistor or number of gates on that chip, based on that, we are going to segregate the integration part. That is SSI. In SSI, we have 10 numbers of transistors, maximum 1 to 10 numbers of transistors and 1 to 12 number of logic gates. MSI, medium scale integration, that will have 10 to 500 numbers of transistors or 13 to 99 logic gates. LSI, large scale integration. In large scale integration, we have 500 to 20,000 transistors. And the number of logic gates are 100 to 10,000 approximately. And in VLSI, we have 20,000 to 1 crore transistors on a single IC. And ULSI, we have 1 crore and more than that. That is nothing but millions of transistors sitting on a single wafer of IC. Then it is called VLSI. Clear, everyone? Next. Yes, sir. Give me a minute break. I'll fetch a glass of water and I'll come back to you. So now the audio is visible, audible, sorry. So coming to the APSCHE design flow. Okay. So as in the first session, we have discussed about if you are considering a chip, okay, for the chip design, we need some specifications and we need some architecture. And for that architecture, we have to generate logic diagram. And for that logic diagram, we have to design an RTL coding. RTL coding is nothing but register transistor level design. That is nothing but using Verilog code or VHDL code or system Verilog code or system C code. We have to do design. Okay. Mainly the design programming languages are Verilog and VHDL. Next is RTL verification. RTL verification, we will be using Verilog, system Verilog, VHDL, and system C. All these are verification programming languages in hardware level. Okay. Next is synthesis. Synthesis is a concept of converting your English Verilog or English VHDL to gate level netlist, which will represent the actual terms of basic gates. This is the concept of synthesis. Next is DFT. DFT is nothing but design for testability. When we are doing synthesis, okay, in the process of synthesis, we have generated the netlist. For that netlist, we will insert design for testability cells. Those cells are called as normal basic gates, normal flip-flops. Okay. So we have a large design. Example, we have a large design. Okay. In this design, we have a small block. This small block is having some misfunctionality. But we have our DFT cells, that is design for testability cells. So we have to debug this chip block why this is misbehaving. So for this, what we will do, we will be passing the test vectors designed for testability. Then we will try to debug the chip misfunctionality by passing the test vectors. This is how the DFT concept is used. There are some different tools in ED applications. Okay. So when DFT comes, I'll explain. Next is floor plan. Floor plan is nothing but we have a chip size. Okay. We have to design the chip area, the IO boundary area. This is IO boundary area, where we are connecting the inputs and outputs of the devices. And this is our area for floor plan. This is completely called chip die. And this is called core area. The complete diagram is die, and the internal part is core, and the intermediate part is IO ring. Okay. So I'll pause for some time. So the RTL verification and RTL synthesis. So RTL verification is nothing but after RTL design. So after RTL design, okay, this is only design. This is Verilog or VHDL. To verify this design, we are going to use RTL verification. That is by using Verilog test bench or VHDL test bench, or by using some Verilog verification methodologies, system Verilog or system C. Using this, we will be writing the test bench and test methodology. Then this is called RTL verification. Once RTL verification is passed, we will be going into synthesis. Synthesis is nothing but process of converting your RTL Verilog code to gate level netlist. This is also in the form of .v. Clear, Sai Shankar? Give me 2 minutes of break.
Sorry, yeah. Too delay, right? Am I audible? Someone please confirm. Yes, yes. Right. So where we are? We are at a stage of floor plan. So in floor plan, what we are going to do? In floor plan, we are going to declare the size of the die, core area, and IO ring. So we are going to do the placement of all the gates in the core area. The core area is filled with standard cells. Standard cells are nothing but the Verilog netlist output generated gates. And if there are any macros, macros are nothing but they are another part of a design. Macro. If we consider an example of system on chip, the system on chip has RAM, ROM, processor, and bus protocols and interfaces. Similarly, we have standard cells that are Verilog netlist gates and macros. Macros are nothing but another chip design that are soft macros or hard macros. Based on the soft macros or hard macros, we will instantiate in the core area. That is called placement. Clear? And after placement, connecting all these nets to the clock pins. That is called clock routing, CTS. Clock tree synthesis. Routing only the clock nets of all the design in the core area is called clock tree synthesis. Audio is not visible. Krishna's Ravani. Am I audible now? Someone please confirm. Is my audio clear? Yes, yes. So next is connecting all the data nets from the flip-flop to flip-flop or the standard cell to standard cell or the macro to macro, connecting all the signal nets. Connecting all the clock nets is clock tree synthesis. Connecting all the signal nets is routing. Next is sign-off checks. That is nothing but we are going to verify the design. That is area, timing, power. All these three things we are going to do in sign-off check. If all these three are meeting, then we are going for fabrication with the foundry. And after fabrication, we will receive a complete chip. That chip we are going for packaging and testing. Already in the initial class, I have told you what is packaging. Packaging is nothing but the silver color pins and the outer layer black color part, making the connectivity for the IO ring of the core chip is called packaging. After receiving the packaging, we are going to put it for testing. Testing is nothing but physically testing using oscilloscopes, network analyzers, or spectrometers, or any kind of appliances. We are going to test the chip. If the chip is successful, we are going to release into the market or going to use in some design. Hope everyone is clear with this. ASIC design flow. So we are going to connect the clock nets. So we have sequential designs, we have macros, and all these designs has internally the clock pins. Either they are positive edge or negative edge. Routing the clock nets is called clock tree synthesis. That is CTS. Clock tree synthesis. CTS is nothing but clock tree synthesis. Clear? Sai Shankar. Okay. Any questions in this slide? You want to understand? So the person who wants to become a physical design engineer should know this concept. So the fabrication after the sign off checks. Sign off checks are nothing but area, timing, power. If these three are passed, then we are going it for fabrication. Fabrication is nothing but we are going to design this IC chip on a silicon wafer. Okay, that is fabrication. CTS means clock tree synthesis. Connecting all the clock nets of your design is called clock tree synthesis. DFT is nothing but design for testability. So design for testability is nothing but we are going to insert scan cells. What are those cells called as? Scan. These scan cells are inserted at the time of placement. Okay. These scan cells are inserted to test the design for testability of the design. If I have a design, this block is not functioning properly. I have these scan cells. Connecting these scan cells, I am passing the test vectors. These test vectors are going to test the scan cells, whether this portion of the chip is working properly or not. If those are passing inputs and processing something and giving the output, then there should be some connectivity issue. In that way, we are going to test the design for testability. Clear, Harini? Yes, sir. So coming to a full chip architecture. Specifications is the first stage. In this stage, the features information which is expected from the customer is collected by some marketing team. So I am an example of an AMD, okay, or an ARM processor. Okay, I have to design ARM processor or Qualcomm Snapdragon processor for our mobile phone. So I have a customer called Samsung or MI. So the marketing person from Qualcomm will connect to the MI or Samsung customer design engineer to get the specifications. This is how specifications are collected from the customer. Next, they are going to give the specifications to the architectural designs, architect of the company. So the architectural team, what they are going to do, they are come up with a block diagram. Okay, the block diagram looks like yellow, green, and blue. Okay, those are the blocks they have designed in the architecture. So completely explaining SoC architecture. So SoC is nothing but system on chip. The system on chip has CPU, GPU, okay, ASIC, and ALU. ALU is nothing but arithmetic logical unit. ASIC is application specific. GPU is graphics. CPU is central processing unit. Okay, and PLL is base lock loop. FM is antenna. RF is antenna, and Bluetooth is antenna. Wi-Fi is antenna, and mic is antenna. Those are all are of analog chip design. The complete SoC is mixed signal chip design. It has covered all digital, all analog, and mixed signal parts. So combinedly these together architecture we are going to build from the specifications. Clear? Any question from this slide? Next. Next is RTL design. ELL is space lock loop. Clock generator circuit. Okay. Next is as per our ASIC design flow, RTL design. RTL design we are going to write in Verilog or VHDL. And next is RTL verification. We are going to verify the RTL design using passing the test benches. Okay. And writing the design methodologies using system Verilog or system C. Next is synthesis. Synthesis is the process of converting your RTL code to gate level netlist for a technology independent design. So if you have a technology, okay, so the technology represents TSMC, UMC, Global Foundries, XME, XFAB, or any kind of technology partner. The technology partner designs process design kits, PDK, or standard cell library. To mapping that technology, we are going to follow the step called synthesis. Hope you are clear. Everyone is clear, right? If you have any question, please post. Venkata Sai Srinivas, gate level code. Gate level code is nothing but after synthesis, mapping to the technology. Okay, so the process design kit or the standard cell library provided by the technology partner. The technology partners are TSMC, Global Foundries, UMC, XFAB, or XME. They are going to give you some library, process design kit. The process design kit is nothing but how you want to design the chip wafer as per your specifications. That is called process design kit. So you mapping to the technology, we are going to fetch the library cells for synthesis to map our Verilog code. That is what called as converting your Verilog code to gate level netlist. The gate level netlist is coming from the library. We are mapping the technology file to our gate level netlist. Sai Shankar, what is FFPQ? FFPQ is the standard cell name. Sorry. So in the right side, we have the netlist. So the netlist is consisting of the standard cell name, flip flop. Okay, that is having D input, clock, and Q output. Okay, that is the standard cell name of the library. NAND, open access, OE, XNOR, inverter. Okay, something like this. These all are standard cells. This is how the gate level netlist look like. Whatever the Verilog code we have written, that Verilog code is English, and the standard cell is mapped to this Verilog code to generate a gate level netlist. Okay, clear? Sai Shankar. Yes. DFT. So as I have said you, we are going to insert scan. So before scan, the combination logic looks like this. And the blue color thing, okay, we are inserting the scan logic. See, OA is not mandatory. Okay, or and. OA is nothing but or and git. So it is not mandatory. Based on the technology library cells available, it is going to map it to OA. Or and. That is the logic. Okay. So coming to the DFT, DFT is nothing but design for testability. So for design for testability, we are going to pass scan cells to the design. So this is before scan and this is after scan. So we have introduced scan in, scan enable, and scan out. These all are introduced at the stage of synthesis and placement. Clear? So the process we use for scanning is ATPG, that is automatic test pattern generation. And one of the logic is LFSR. Next is floor plan. Floor plan is nothing but we are going to decide the die and core area. And the blue color lines are called follow pins. Okay. Based on the height and width of the die, we are going to decide the aspect ratio. The aspect ratio is nothing but height by width of the die area. Next is core utilization. The core utilization is nothing but the inner chip area. How we are going to utilize by placing the standard cells, by placing the macros. Okay, that is how the core utilization is calculated. Standard cell area plus macros area divided by total core area. This will give you the core utilization. The core utilization should be every time 60 to 70%. The remaining 30% is used for clock tree synthesis, signal routing, and sign-off checks. Clear? And in this, the space between die and core area is called IO. IO ring area. Clear? Any question? Continue. Yes? No? Okay? Yes, sir. After floor plan, what we are going to do? We are going to place the standard cells. Okay? So all these are standard cells. Those standard cells are globally placed. Globally placed means just they are called for placement. So based on the standard cell height and width, we have the fallow lines, the blue color lines, which are in the core area. Based on that lines, we are going to detail do the placement of standard cells in the core area. So these are randomly placed. They are not placed between the two lines. Here they are placed between the two lines. That is, height and width of the standard cell are adjusted in between the core area. Clear? And in the placement stage, we are going to check about congestion and timing. Congestion is nothing but how the standard cells are placed. Are they very congested or very flexible for routing and clock tree synthesis? As the cells are placed, we are going for the initial timing analysis. The timing analysis, we call it as static timing analysis, STA. There is an engineer called STA in VLSI industry. Okay, clear so far? Right. Next is clock tree synthesis. So this is a famous diagram in the internet where it is coming from my bachelor's in engineering. Okay, so the same diagram here also I am explaining. So in the core area, we will be having the clock source pin. Source pin is nothing but when we connect it to the PLL or when we connect it to the crystal oscillator, it will generate clock. That clock pin is called clock source pin. And all these yellow color, these are standard cells which are placed in core area. And routing the nets to each and every clock pin of the standard cell, that is called clock tree synthesis. And there are different types of clock tree algorithms. The most one is used is balancing clock tree. When we turn on the clock, it has to reach the clock signal to all the flops or all the standard cells which are in the core area in equal amount of time. Then only it is called clock tree synthesis. If it is not reaching, then we have some clock skew. The clock skew can be positive or the clock skew can be negative. That is, the clock is reaching this flip-flop with delay and this flip-flop with positive delay. Then it is called clock skew. So only we are going to build a clock tree synthesis of balanced tree structure, which will reach all the edges of the flops in equal amount of time from the source pin to all the clock pins. Clear so far? What is clock tree synthesis? Someone please confirm. Hope everyone understood what is clock tree synthesis. Clock skew is nothing but, see, from the source pin, I am routing the clock pin to the distant flop. Okay, this is reaching in longer time. Then it is taking longer time. When it is reaching to the nearest flip-flop, it is reaching very soon. Okay, but what is my clock tree synthesis motto? It has to reach all the flops in equal amount of time. Then the difference is called clock skew. Clear? Sai Shankar. Yes, Sai Shankar, you are paying very much attention in learning these things. Ram Babu, thank you. Should I proceed for next slide? Yes, sir, Ram Babu. Suresh. Next is routing. So after doing the placement, after doing the clock tree synthesis, okay, so we are going to have the signal nets routing. The signal nets routing has some rules and regulations. They should have minimum width of the net, minimum height of the net. Okay, they should route in a straight direction. They should not be a curved direction. Okay, So like that, we are going to do two types of routing, global routing and detailed routing. Global routing is nothing but we will do it for test. Like we just route and see how much routing area it is taking. We will estimate the congestion. We will estimate the area. We will estimate the violations like net to net cross touching, net to net short, and all those things. And avoiding all this, we are going to do the detailed routing. Once the detailed routing is done, we are going to do physical verification. Physical verification is nothing but we are going to check DRC, design rule check, LVS. LVS is nothing but layout versus schematic. This kind of design is called layout. And the logical diagram we have seen is called schematic. If those both are similar, then our design is successful. If not, we have to go and modify in the layout. Clear? So far, the explanation, everyone followed me? Yes. Navani. Done. Next is timing sign off. The timing sign off is we are going to use what are the timing sign off? Area, timing, and hour. All these are called as sign off checks. So among these, the most important one is sign off timing analysis. So what we will be doing? We are going to generate standard parasitic extract format, SPEF file. So after DRC, LVS, we are going to do PEX. PEX is nothing but parasitic extraction. We are going to calculate the net. This is some net. This has some resistance and capacitance. We are going to extract all the nets RC values using PEX. The tools used for PEX are Caliber, Asura. Caliber is from Mentor Graphics and Asura is from Cadence and Star RCXC from Synopsys. So using this PEX, we are going to generate standard parasitic extraction file. This standard parasitic extraction file, we are going to use some tool that is called Tempus or Primetime. Tempus is from Cadence and Primetime is from Synopsys. Okay. Standard parasitic extraction format, SPEF. These files we are going to give to the tool input Tempus and Primetime, either of the one. And we are going to check the timing sign off analysis, whether my design timing is meeting or not. If it is not meeting, we are going to check the LVS or DRC and PEX one more. If all these are passed, okay, we are going to do logical equivalence checking. Logical equivalence checking is nothing but Verilog code and Verilog code after routing. This is design Verilog code and this is routed Verilog netlist. Both we are going to do LEC, logical equivalence check. If this logical equivalence check is passed and quality, then we are going to do tape out, that is fabrication. We are going to give the chip for manufacturing. Clear? Understood everyone? DRC is nothing but, so foundry has, the fabrication lab has some rules. If my design has some 6 metal layer design, Okay, 6-metal layer design is nothing but poly M1 to M5. So poly is nothing but base metal layer. So here we will have only gates connected, the transistors. M1 is used for nets or signals connection. M2, M3 is used for, M4 is used for routing. And M4 and M5 are used for power. Basically, assume. Okay. So each and every net in these areas should have some thickness, should have some wide, and should have some length. So all these are called design rules. These design rules are defined by PDK or foundry. Chip design foundries. Those people will be giving you the design rules check file. We are giving it to the tool, Caliber or Asura, okay, for sign-off analysis for DRC. The design rule file as the input. If the design rule file has passed, okay, then here DRC pass. If the DRC is passed, we are going to check for LVS. LVS is nothing but layout versus schematic. So whatever the logical diagram we have, that logical diagram we are going to compare with layout. Layout is nothing but final routed netlist. Both we are going to compare, and if this is also passed, then we are going to do text extraction. Text extraction we are going to do, and we are going to do sign-off timing analysis, area analysis, and power analysis. And if this everything pass, we are going to do chip fabrication. Clear? Hope everything understood. Tarak. Mr. Tarak. Gupta, yes sir. Shiva, yes sir. Tarak, yes sir. Thank you, Tarak. So these are the different tools from EDA. Okay. For layout, custom compiler. These all are synopsis based tools, whatever I'm giving. Okay. Layout is for custom compiler. Synthesis, design compiler. Placement and routing, ICC2 or ICC. Okay. For text extraction, star RC. STA, timing analysis, prime time. And physical verification, ICV. And power side timing analysis, prime power. These all are the different tool names used from synopsis for doing these tasks in the ASIC design flow. So in the next class, I'm going to teach you about synthesis in detail. Okay. For now, this much is fine for today. So if you have any questions, please proceed. So I can give you the names of cadence tools also. Cadence for the layout is Virtuoso. Synthesis, Genus. Placement and routing, Innovus. RC extraction, Asura or Quantus. Timing analysis, Tempus. Physical verification, PVS. Power analysis, Voltas. These all are the tools from Cadence. Okay, everyone followed? Understood? Clear? Any questions, please ask me. I'll wait for 2 minutes. Navanit Kumar, is there any manual override technique for microprocessor? What is the meaning of manual override technique? Standard parasitic extraction format, SPEF. Navanit, I didn't understand what is manual override technique for microprocessor. Jayshree, SPEF stands for Standard Parasitic Extraction Format, SPEF. Any more questions? Inter-integrated circuit 2, that is ICC compiler. Integrated circuit compiler, IC compiler. That is a standard cell length, FFPQ. Mille ABCD example, I'm not sure the practical example, but the mixed FSM example is like we are controlling the escalator or lift or the coffee machine also sometimes. Okay, analyze, I think. If you have any example, please let me know. Mille FSM. I don't remember exactly. It's too long back. Okay, that's all from my side.